Okay, so I'm in the 150-pound man on a cushion, coefficient of static friction given. Basically, this is rotating around a central axis. This is like a fair ride, right? Uh, what we want to determine here is what's the smallest angle so this guy doesn't go flying off the back end, right? Because if I make it too shallow, he'll slip right up that incline and get injured probably, right? So let's go ahead and start by drawing a free body diagram here. So what I have here is the dude's weight, which is 150 newtons. Okay. I have the friction force. And again, as this starts accelerating and spinning, he's going to want to slide up that incline. So the friction is going to oppose that and go right back down. And again, I'm trying to find at its maximum point. I don't want him to slip, right? But I want the point right before he starts slipping. So I'm going to put that friction force at 0.5 n, which tells me also I have a normal force that I've got to include as well on this. Okay, and what I'm going to recognize is that this angle right here is actually my angle theta given here. Now, what I need to do is I need to recognize that my normal direction is actually a horizontal direction. This is going around a path. So it's not in the same direction as my normal force, right? We think about acceleration when we set up our axes. This guy's going to be going on a circle, a horizontal circle. So my acceleration is towards the center of that circle, which will be a horizontal axis towards the center, n as shown there. Uh, then I'll have a z-axis going straight up. My tangential axis will be coming straight out of the page into the face. Okay, so again, don't make the mistake of setting your normal uh, direction in the same direction as your normal force. You want to set it up based on acceleration. Okay, and he's accelerating. The normal acceleration is towards the center, straight to the left, because it's a horizontal circle that they're going around here. Okay, so from that, we'll go ahead and sum my forces in that normal direction. Okay, and I'm going to have n sine of theta. Okay, and then I'm going to have my friction force, which will be cosine of the theta. And again, I'm at the maximum friction force. That's why I use 0.5 n. Okay, and this is going to equal the mass times the acceleration in the normal direction. So it's 150 pounds divided by 32.2. That gives me my mass, right? So I got to get it into slugs. Okay, and it is the velocity is 30 feet per second. So I square that and I divide by the radius, which is given to be 8 feet here. And real, oh no, I've got my normal force. So that's one equation. Do the same thing in the z equation where I have negative 150, the weight of the dude, straight down. And then I've got n cosine of the theta. And then minus the friction, which would be sine of theta. Okay, acceleration here is 0, and this is the whole point of setting up my axes in this way, because we don't want this guy to accelerate. We want the only acceleration to be going on towards the center in that normal direction. I don't want any acceleration, otherwise he'd be slipping. So there is no z component of acceleration, and I can just get rid of that like that. Okay, two equations, two unknowns. Okay, I can, well, I kind of have to solve them in concert. Not the easiest set of equations. Okay, calculators will solve them for you. I get an n of 488, and then I can solve my theta, 47.5. So any smaller angle than that, he's actually going to start slipping. Okay, anything bigger than that, he'll be fine. He'll just kind of stick to the wall, and everything will be fine. So again, free body diagram, set up your axes based on what we know about acceleration, and then apply your equations of motions and solve.